In the earlier lecture, we were looking at superconductor normal interface, okay, and for x greater than 0, this was the superconductor and superconductor vacuum interface, okay, and this is all empty, okay, and this is the point x is equal to 0, and we were writing down the GL equation in the zero magnetic field, and there we had come across so the entire spatial dependence of the wave function was expressed as xi naught, where this is the equilibrium value of minus alpha by beta, okay. This is your equilibrium value of the Ginzburg-Landau functional, and this is all the spatial dependence multiplied by fx, where fx contains all the spatial dependence. So this minus alpha by beta is the equilibrium value, and then as you approach the boundary, there will be variation in the order parameter, and that variation is encoded in this function fx. So if we write down through the first GL equation our equation, then we will have an equation for f, which is d square f by xi square d square f by dx square plus f into 1 minus f square is equal to 0, where xi turned out to be a quantity which is minus h cross square by 4m alpha, okay. And this negative sign basically for t less than tc, this goes into alpha, okay, it gets absorbed into alpha, and you will get tc minus t, okay, depending, because this Ginzburg-Landau parameter has a temperature dependence alpha which is equal to a t minus tc, okay. So you can actually write down this expression and you can find out. So xi square has units of length, okay, xi square has units of length, and you can length square, actually it has units of length square, so you can non-dimensionalize this expression, the above differential equation, by considering this parameter eta, which is x by xi, and then you will have a non-dimensional differential equation f into 1 minus f square is equal to 0. And then we would like to interpret this behavior of this function, okay. So d square f by d eta square plus f minus f cube is equal to 0. We will just try to reconstruct this equation in a different form, okay. So what you do is that you multiply this by df by d eta. So df by d eta, d square f by d eta square plus df by d eta f minus df by d eta f cube is equal to 0, and then you integrate the above equation over eta, okay. So you will have terms like df by d eta. I just show you some typical calculation. Df by d eta square, d eta will be df by d eta, df by d eta, integration by parts. If you do integration by parts, minus integral d square f by d eta square into df by d eta d eta. And now these two expressions are exactly identical, so you take them on the other side. So integral of df by d eta, d square f by d eta square, d eta will be half of df by d eta the whole square, okay. Similarly you can do for the others. So if you do the same thing for the others, then you will find that we write the above differential equation. This differential equation, if you do an integration and you do this integration by parts, then your expression becomes half of df by d eta the whole square plus half of f square minus 1/4 of f raised to 4 is equal to a constant. This is the constant of integration. Constant of integration. Okay, or or df by d eta the whole square plus f square minus half f raised to 4 is equal to a constant. Okay, now we put boundary conditions. For the vacuum superconductor interface. So you have a vacuum superconductor interface. This is superconductor x greater than 0, x less than 0, you have vacuum. Okay, and what we say is that this eta is 0 at x equal to 0. At x equal to 0, the moment you reach at the interface, nothing can leak out because it is vacuum. Okay, this is completely vacuum, so there can be no leakage of the superconducting state into vacuum. Okay, so this eta is equal to 0 at x equal to 0. And so eta is equal to 0 at x equal to 0, and f will be 0 at this point. Okay, so at this point where eta is equal to 0, the function f has to be 0. The order parameter has to go to 0. So the order parameter has to be 0, that is f is equal to 0 at the vacuum superconductor interface x equal to 0 or eta equal to 0. This is your first boundary condition. Now the second boundary condition is that if one is very far from the interface, then the order parameter is uniform or no spatial dependence. Namely, if you are at this is the superconducting side, this is your vacuum side, x less than 0, x greater than 0, x equal to 0. If you're far away from the interface, if you're very far from the interface, then we take that the order parameter is flat. The order parameter is flat and no spatial dependence, which is reasonable thing to do. That is df by d eta is equal to 0. So the second condition is that for eta tending to infinity, df by d eta is equal to 0. So this is your second condition. So the first condition is that at the interface the function goes to 0, and far away from the interface your order parameter is absolutely flat and spatially has no spatial dependence. So the derivative of this quantity f, which encodes the spatial dependence of the order parameter, that is equal to 0. The spatial derivative of this function f is 0 at infinity, or f is equal to 1 at eta tending to infinity. This is also another condition that you use. That means psi is equal to psi naught into f implies that at n tending to infinity, psi is equal to psi naught. which is square root of minus alpha by beta. Alpha is anyway a t minus tc. Okay, so for t less than tc, okay, this minus alpha will make it tc minus t. Okay, so if far away from the interface, okay, this tells that the far away from the interface, the order parameter is fixed at its equilibrium value. Minimum value, that is psi naught square is minus alpha by beta. Okay, so f is equal to 1. Okay, so f is equal to 1 at far away from the interface. Then the wave function or the order parameter is fixed at its minimum value, which is minus alpha, minimum equilibrated value, which is minus alpha by beta. Okay, so with this condition, let us look at this expression d square f by d eta square plus f minus half f raised to 4 equal to a constant. And for eta, sorry, just let me correct this expression, 1 second. For eta tending to infinity, f is equal to 1 and df by d eta is equal to 0. So we will get a condition that constant is equal to half. Because this will be 1, you will be substituting 1 out here and this will be 0. So you will evaluate your constant equal to half, and then based on this expression you will get d square f by d eta square df by d eta the whole square is equal to half of 1 minus f square the whole square. If you substitute this constant out here and if you rearrange the terms, then you can write down this f square minus half f raised to 4 equal to half can be again rewritten like this. Okay, and the solution of the above equation is f is equal to tan hyperbolic eta by this is the form of the expression of f of x, this function f of x, or f of x, this is f of eta is x by xi. So f of x is equal to tan hyperbolic x by root 2 xi. This is f of eta, it is eta by tan hyperbolic eta by root 2. So this is how the function behaves. Psi x is equal to psi naught tan hyperbolic xi, where this is basically coming from the expression psi is equal to psi naught into f, where psi naught is the equilibrium GL minima value in superconducting state. Okay, and xi square is equal to minus h cross square by 4m alpha. Okay, now if I plot this function, okay, so this is xi is equal to where xi naught square is nothing else but minus alpha by beta, or you can rewrite this above expression xi x as equal to xi infinity tan hyperbolic x by square root of 2 into xi, where xi infinity is the value of the order parameter far away from interface, and it is equal to xi naught, which is minus alpha by beta square root. Okay, and minus alpha is nothing else but a Tc minus T for T less than Tc. Now, if I look at this behavior of the order parameter, then the tan hyperbolic behavior, then far away, this is x and this is psi. Okay, far away the function is constant, that is the form of tan hyperbolic. This function is nothing else but psi naught, and as you approach this, as you approach closer to the, so this is the superconductor, this is vacuum. As you approach this boundary, the order parameter drops to 0, and the behavior of the order parameter, this is, it goes to 0. The behavior of the order parameter here is tan hyperbolic x by root 2 xi, and the length scale over which it decays, this length scale is the Ginzburg-Landau coherence length. Okay, xi is the, it is written as xi GL, is the Ginzburg-Landau coherence length of a superconductor. It is the distance over which so the Ginzburg-Landau coherence length is the distance over which the superconducting order parameter goes to 0 as one approaches a superconductor vacuum boundary. Okay, so the distance xi over which the order parameter actually goes to 0. So as you are away, so far away from this interface, the order parameter is at its fixed value and it is at xi naught, which is the equilibrium value. Mod of xi naught square is minus alpha by beta, which is obtained from the minima condition of the free energy. If you minimize it with respect to the order parameter in zero magnetic field, then you will get minus alpha by beta for xi naught square. So it is fixed at that value, far away from the interface, deep inside the superconducting state. But as you approach the superconducting to vacuum boundary, then here the superconductivity, the order parameter has to go to 0, because at the boundary the superconductivity is lost completely. Just outside the boundary there is no superconductivity left to define. So at the boundary the order parameter has to be 0, and the distance over which it goes to 0 is the coherence length, the Ginzburg-Landau coherence length. This Ginzburg-Landau coherence length xi GL square is minus h cross square by 4m alpha. You can also write it as h cross square by 4m mod alpha. Okay, the negative sign, because alpha can be written as minus mod alpha, where mod alpha is a Tc minus T for T less than Tc. Okay, so you can resubstitute this here, and this will give you hc square by h square by 4m a Tc minus T. So the coherence length xi GL goes as h cross square by 4m a into Tc raised to half 1 minus t raised to minus a half. Okay. So if I plot the behavior of the coherence length equal to T by Tc. So if I plot the behavior of the Ginzburg-Landau coherence length as a function of temperature T by Tc, then if this is 1, namely T equal to Tc, the coherence length is going to be flat. Far away doesn't have much temperature dependence, but its temperature dependence is going to diverge as you approach the superconducting normal superconducting vacuum interface. At Tc, the coherence length is going to diverge. Okay, it spans the entire superconductor, namely that the order parameter varies over the entire superconductor when you approach the Tc, which is understandable because now the superconductor has turned normal. So there is no equilibrium value of minus alpha by beta anywhere inside the superconductor. So the coherence length, the order parameter, is now completely varying over the entire superconductor, and so your xi is tends to infinity as you approach Tc. So this is the interpretation. So you get one length scale, which is the Ginzburg-Landau coherence length, and this Ginzburg-Landau coherence length is related to your superconducting BCS theory coherence length. It also has a similar connotation, that if you, from the BCS theory, if you try to derive the Ginzburg-Landau theory, people have done it, that from BCS theory they try to derive the Ginzburg-Landau theory. Then if you do that, you will see the connection between the xi BCS and the Ginzburg-Landau. They have similar interpretation. Whereas in the BCS theory, the xi corresponded to the size of the Cooper pair. In the case of Ginzburg-Landau, where you are defining an order parameter, the distance over which the order parameter is going to decay as you approach a normal superconductor interface. So the distance over which the order parameter xi decays as you approach the normal superconductor interface, this distance xi is the Ginzburg-Landau coherence length, which is approximately also similar to the size of Cooper pair in BCS theory. Okay, so this is one fundamental length scale that we derive out of the Ginzburg-Landau theory. Okay, now very quickly we can also get a second length scale in the Ginzburg-Landau. Second length scale theory, and this second length scale comes from the second G equation. I will very quickly work that out. Is J is equal to H cross minus IE H cross by 2m psi star gradient psi minus psi gradient psi star minus 2 E square by m vector potential A into psi naught psi square. Okay, this you have already seen. Now psi is equal to psi naught E raised to I phi, and this term we had worked it out that it is equal to 2I mod of psi naught gradient of phi. Okay, so if you put this expression there, J is equal to, you will get H cross E by 2m mod of psi naught square gradient of phi minus 2 E square by m vector potential A mod psi naught square. Okay, now what you have here is, so far away deep inside the superconducting state, where psi is equal to psi naught and uniform, this is the equilibrium value of minus alpha by beta, or mod of psi naught square is equal to minus alpha by beta. So deep in the superconducting state, where you are far away from any such where you have a uniform value, your gradient of phi is constant, is 0. Okay, there is no spatial dependence that you can consider of the phase factor phi is a constant, and then J is nothing else but, so if you don't consider any spatial dependence of the phase, J is nothing else but 2e square mod of psi naught square by m. Of course there is a mu naught out here, you can put that mu naught here. Okay, and this is into the potential A. Okay, and what is alpha? Mod of psi naught square is which is equal to mod alpha by beta, where alpha is equal to minus mod of alpha. Mod of alpha is A Tc minus T excuse me, this is Tc minus T, Tc as T minus T for less than Tc. So you can write alpha as minus of alpha, mod of alpha, where mod of alpha you can appropriately rewrite like this, and so this is how psi naught square will be. And so Js is nothing else but minus 2e square by m mu naught mod alpha times the vector potential. And now this seems to be, if you have a vector potential applied with a magnetic field to the superconductor, then what you will find, so if you apply a magnetic field to the superconductor, then the superconductor will respond with a current density which is 1 by lambda GL the whole square into the vector potential. Dimensionally this lambda is also length square. If you try to balance the dimensions in this expression, this lambda GL the square is nothing else but m mu by 2e square mod psi naught square. This anyway is density of Cooper pairs. If you see that this lambda is very reminiscent of penetration. So so you see that Js is minus 1 by lambda GL the whole square into the vector potential, where lambda square is m mu naught by 2e square mod of psi naught square, where psi naught square is nothing else but your density of Cooper pairs. And you can also write this as m by mu naught. If you write it in terms of GL parameters, it is 2e square beta by mod of alpha, because mod of psi naught square, this is also equal to mod of alpha by beta. Okay, so so I'm sorry, so here it should be mod of alpha by beta. Yes, okay, so this would be your lambda GL the whole square. Okay, and if you look at this expression, J is minus 1 by lambda GL the whole square times vector potential. If I take the curl on both sides, then curl of Js is equal to minus 1 by lambda square curl of A bar, and this of course is curl of B. You can write the current density, so curl of B is minus 1 by lambda square B. This is anyway B, and this would therefore give me this with divergence of B is equal to 0 will give me del square B is 1 by lambda square, del square B is 1 by lambda GL the whole square B. This is basically your London's equation, okay, where lambda GL square is where lambda GL is nothing else but the penetration depth. So not only do you get information about xi GL, which is the Ginzburg-Landau coherence length, which is the length scale over which this is vacuum superconductor, the length scale over which the order parameter goes to 0 as you approach a superconducting boundary, okay. Okay, so this is flat far away from the boundary, it is flat, and then as you approach the boundary it decays from its minima value, and the order parameter decays from its minima value, and the length scale over which it decays as it approaches the boundary is the Ginzburg-Landau coherence length, which is also related to the size of your Cooper pair in the BCS theory. And similarly, from the current density, the supercurrent density from the second equation, from the second GL equation, the supercurrent density, if you take a superconductor, a uniform superconductor, if you take a uniform superconductor and place it in a magnetic field, then the supercurrent density is Js is minus 1 by lambda square A bar, and this is your London's equation, and lambda GL, this is your lambda GL, gives your penetration depth. So from your GL equations you get two fundamental length scales which you can derive. One is xi GL and one is lambda GL, both of which are related to the microscopic parameters which you are already discussed, okay. Both of these are related, and lambda, if you see, lambda GL, if you see, is m mu naught by 2 e square mod of alpha by beta, and mod of alpha is nothing else but Tc minus T for T less than Tc. So this is lambda GL square would be m mu naught beta by 2 e square a Tc minus T, or lambda GL will be proportional to 1 minus T raised to minus a half, where T is equal to T by Tc. Okay, you can directly show it here. You take Tc out common and you will get this factor T. So if you are looking at the behavior of lambda GL as a function of temperature, and this is your Tc, it is going to be a constant value, and then as you approach the superconducting transition, lambda GL diverges, okay, and it goes as this divergence is 1 minus T raised to minus half as T tends to Tc, and the basic meaning is that once you are approaching the superconducting transition temperature, magnetic field is going to penetrate all across the superconductor, and because the superconductor is taken to be infinite without any surfaces, therefore lambda will become infinite. So as you approach Tc, the magnetic field will penetrate all over the superconductor, and as the superconductor is infinite, no surfaces, therefore your lambda GL tends to infinity at Tc. And similarly is for the coherence length GL, is that the order parameter then changes at Tc, order parameter, even lambda changes at Tc. The order parameter, it spreads over the, it varies over the entire sample because superconductivity is lost, okay, and therefore lambda GL also tends to infinity, xi GL, the coherence length also tends to infinity. Both lambda GL and xi GL is 1 minus t raised to minus half, and lambda GL is also proportional to 1 minus t raised to minus half. Both of this come from the GL equations. Okay, so you get fundamental length scales which are related to the microscopic length scales which you have already derived. The BCS, the Ginzburg-Landau theory also gives you the same length scales, but it is very easy to derive their temperature dependence. With GL theory, it is easy to get the temperature dependence of the fundamental length scales.